So what we're going to talk about or introduce today is something called instantaneous velocity, or velocity at just one value. And so what ends up happening is, I'm going to talk about where this comes from, but if you try to find the velocity at one value, like at 5 seconds, in the velocity formula you would end up dividing by 0, and so you can't do that. So instead what we do is we try to find the limit as you get to 0, and so we're going to be using then some of the things that we worked on the last few days to evaluate those limits. So let's just first review. Everybody hopefully knows this. What's the formula for average velocity? So how would I find that? Yeah, it's just the change in position, right? Which is, you're right, the change in the distance, how far something traveled, divided by the change in the time. In science, you've probably seen the symbol delta before. Okay, delta is looks like a triangle, but it's the symbol for change in. And also in science, I don't know if you've seen this before, that positions are usually denoted with S. So if I say the change in S, that just means the change in position, and then over delta t, so the change in time. So good. So if I said to you that a car travels 500 kilometers in 4.5 hours, what is its average velocity? And so what would you do to find that? You just take, yep, change in position. Well, if it went 500 kilometers, that means this change in position was 500 kilometers. And how long did it take? It took 4.5 hours. And you divide those two. What's 500 divided by 4.5? 4.5. It's 111 point repeating?
111.
Okay. So the question I'm going to pose to you then is, during that 4.5 hours, was the car going 500 kilometers per hour the whole time? Okay, no. I mean, it's just going to give us that average. Okay, so we don't know what the different speeds were of the car, okay, but we do know because that's how far it traveled over that time period. So the difference between average velocity, which you already know, and something called instantaneous velocity. This would just be the velocity at a specific time. So if I wanted to know, for instance, let's say I even told you, hey, that a car starts at 5 meters and then at 1 second, and then at 1.5 seconds it's at 10 meters. You could do an average velocity still, because you have 2 values and 2 time values. But on the bottom, what you would have done was subtract the 1 and the 1.5. Agreed? But if I said, hey, what was its instantaneous velocity at 1 second, do you see how I don't have a change in time then? I'm just saying at 1. And so what mathematicians discovered is there's a way that we can try to figure that out. And that is really where, this is kind of the basis of where calculus actually comes from, is this problem, okay? So we're going to take a look at this, and we're going to zoom in at a certain point, and then what you're going to see, hopefully, is that it's going to be evaluated using a limit. So let's say, for my instantaneous velocity, I'm going to tell you that a ball rolls 16 feet in 4 seconds. Okay, so let's just calculate in our heads what's the average velocity then in that 4 seconds. Yeah, and I'll write that as V average is 16 divided by 4, or 4 feet per second. But what if I then asked, that's what we're going to try to find, what is the instantaneous velocity at 3 seconds? And so this is really going to drive the rest of what we're going to do in class today. What is the instantaneous velocity at 3 seconds? Can we find a value that's so close? So what we're going to assume for this is, first of all, you could do this because this is really 0 to 4 seconds. That's its change in time. I don't mean what's its velocity in the first 3 seconds. I mean right at the instant, at 3 seconds, what is its velocity? That's what I'm asking. So I can't do this with the average velocity formula, because what I would do is I would say, oh, the change in time would be, wait a second, 3 minus 3. Can't divide by 3. So first what I'm going to give you is a position equation. So we're going to assume that the position of the ball is just going to be t squared for right now. Okay, so we're going to define how far the ball goes by putting in the time squared. So what I'm going to do is, and then I'm going to do this on a small interval. So for instance, what if I could use the average velocity formula on an interval close to 3? And so what I'm going to use is the interval 3 to 3.1 first. Okay, and we're going to see if we can figure out what the velocity gets close to. So if I did the change in position over the change in time, remember this is my position equation, right? Okay, so wouldn't the change in position be 3.1 squared minus 3 squared? Because this would be its position at 3.1 seconds, and this would be its position at 3 seconds. And what would the change in time be? What would the change in time be? 3.1 minus 3. Can you guys get your calculators out for me and tell me exactly what do we get on top? Is it 0.61 divided by 0.1, which is, okay, feet per second. Oh, I can squeeze it in. Okay, and then highlight that or circle that a second. That's on this interval. All right. Let's see if we can get a little bit smaller. So I did just 3 to 3.1. I'm going to cut that interval in half. I'm going to try to see if there's a pattern here and I can find what this is getting close to, its limit. So let's cut the interval in half. Now let's try from 3 to 3.05. Okay? So we're going to do the formula again. So on top, what are we going to do? 3.05 squared, good, minus 3 squared. And on the bottom, we're going to do 3.05 minus 3. Okay, can somebody tell me what you get on the top? 0.0325? No, 3025. Okay, when you divide it, those two numbers, what do we get? 6.05 feet per second. Okay. Okay, I know we could keep doing this. I'm going to do it one more time. Okay? So I'm now going to cut this interval in half, or not as, what did that be in half? No, I'm not going to cut it in half. I'm just going to decrease it by 1/100th. So I'm going to change this to 3.005 now. Can you guys tell me what you get for this? Okay, and when you divide it by 0.005, 0.005? Okay, so if you were to make an educated guess, what do you think is going to happen as I continue? I'm not going to do it again, but if I were, let's say, made this smaller still, and that's a small interval of time, right? But it does allow me to divide by a number that's not 0. What do you think I would get? Yeah. Now, I couldn't get to 6 because I can't do 3 minus 3 on the bottom. But you would, and we call that a what? A limit, okay? And so let me show you algebraically then why this would be 6. So learning what we did before, if I said, what's the limit as t gets to 3? And what were we doing on top? We were doing this squared minus 3 squared, agreed? So we were doing, in general, t squared minus 3 squared. And then what were we doing on the bottom? T minus 3. So, how could we, or how have we learned over the past few days that I could find that limit then? This is really t squared minus 9. You're right. So the top really is t squared minus 9. The bottom is really t minus 3. What could we do with the top? T minus 3 over t plus 3. Then what happens? We cancel. So t plus 3, when we put that 3 in, we get 3 plus 3, or 6. So what you guys have done is actually found the instantaneous velocity. You've done your first derivative of calculus, actually. Okay? So, really what we're going to be doing today is we're finding, and that's what you got to remember, we're finding velocity at a point, and we're going to be using limits to evaluate that because it's impossible to divide by that small of an interval, impossible to divide by an interval of 0. Okay, so how